Okay, so today we're going to talk about section 9.1 in your textbook, and this is on sequences. This is just an introduction to sequences, and I think most of this will be a refresher for you once you see it. We'll start with a simple example just to remind you about notation involving sequences. So here we're looking at the first four terms of this sequence. Now they've named the sequence a sub n, and we're going to find each term by taking 3 plus negative 1 to the n power. So we're always going to start our sequences, just for simplicity's sake, at where n equals 1. In pre-calc, you might have started them at 0, and sometimes we'll do that, but generally speaking, we'll start where n equals 1. So if we calculate a sub 1, plugging in 1 for the n value, we get 2. A sub 2, you'll see we get 4. A sub 3, we get 2. And then a sub 4, we get 4. So this is one of those sequences that's going to just go back and forth between 2 and 4. How about this sequence? We're naming it b sub n, and it's defined by n over 1 minus 2n. So if we plug in 1 for the n value, b sub 1 turns out to be negative 1. B sub 2 turns out to be negative 2/3. Plug in 3 for the n value, we get negative 3/5. And if we plug in 4 for the n value, we get negative 4/7. So for many sequences, the terms will approach what we say a limiting value. And if that happens, if the sequence converges or approaches a limiting value, we say that it converges. Consider this sequence, b sub n equals 1 over 2 to the n. When we say approaches a limiting value, what we mean is as n goes to infinity. So think about, if we put in values for n, starting with n equals 1, we have 1/2. If n is 2, we have 1/4. N equals 3, we have 1/8, etc. You can see what's going on. As n goes to infinity, as n gets large, the fraction approaches what? 0. So we would say the numbers in this sequence converge to 0. And we could also write this as the limit of the sequence as n goes to infinity. And you can see clearly that that would be 0. A little sketch from the book that talks about what's going on. As n goes out to infinity, we can see the values will get closer and closer. They may go above and below, but they'll get closer and closer to that limiting value. If the sequence has no such limit, then we say that the sequence diverges. Let's take a look at another example. Find the limit of the sequence whose nth term is given by this expression. So as soon as you see this question where they ask you to take the limit of the sequence, they're really talking about the limit as n goes to infinity. And hopefully, if you remember from the last test, this expression looks somewhat familiar to you by now. Remember, we used L'Hopital's rule to evaluate this limit as n goes to infinity. Now, I told you in this chapter, you don't have to show me all the steps. You can just memorize what this is. Do you remember what this limit is? Remember that it was e, so whatever was the numerator for this fraction. In this case, that's 1. So the limit for this is e. In this example, we would say that the sequence converges to e. So all of the usual properties involving limits from functions will also apply to any limits involving sequences. Let's do a couple more limits. So evaluate the limit of the sequence or determine that it diverges. This was that sequence we had earlier, and if you remember that the terms we had went between 2 and 4, 2 and 4. Sort of an alternating sequence that alternated between 2 and 4. So is there a limit for this as n goes to infinity? No, there's not, because it's just going to go back and forth between 2 and 4. We would say the sequence diverges. Try another one. I think this was the one we were looking at earlier. Just think about what happens here as n goes to infinity. Of course, we could apply L'Hopital's rule, but remember we also can compare the degree of the numerator to the degree of the denominator here, because this is just a rational function. Since the degrees are the same, this limit will approach negative 1/2. So we would say this sequence converges to negative 1/2. Try this one. And if we took the limit for this as n goes to infinity, we could think of this as infinity over infinity, and we could apply L'Hopital's rule to it. But remember last year we talked about growth rates. Which of these grows faster, the polynomial or the exponential function? The exponential function grows faster, and that's on the bottom. We would say that this goes to 0. So this limit converges to 0. Okay, so the next thing I want to talk about is something called the absolute value theorem for sequences. And this theorem says that for the sequence a sub n, if the limit as n goes to infinity of the absolute value of the sequence goes to 0, then the limit of the sequence also goes to 0. This would be useful if we've got a term that involves, or a sequence that involves negative terms. We can evaluate the limit of the positive terms only, and it goes to 0, then that tells us that the original sequence also goes to 0. Look at a quick little example here. We've got the alternating sequence, 1 over n factorial. Think about what would the absolute value of a sub n be. It would be 1 over n factorial. Take off the alternating part. And if I said to you, take the limit of that absolute value of a sub n, you can see pretty quickly that this goes to 0 because the denominator is going to get really large, which means the fraction is going to get really small. So since this sequence we know goes to 0, what does this theorem tell us about the original sequence that included the alternating part? It also goes to 0. Picture of the graph of the sequence. Okay, so let's look at this example. Find a sequence, a sub n, for the first 5 terms that are given, and decide if it converges or diverges. So if you think back to pre-calc, every once in a while you had some problems where they would give you terms in a sequence and you had to come up with the expression for it. So look at these terms for a second and see if you can see what the pattern is. One thing to observe is that all of the numerators are powers of 2. 2 to the first, 2 to the second, 2 to the third. And the denominator are all successive odd integers, 1, 3, 5, 7, 9. How can we express that? We're going to write this as 2 to the n over 2n minus 1. 2n minus 1 would take an even integer and just subtract 1 from it, which is where the 1, 3, 5, 7, 9 would come from. If I said to you, does this converge or diverge? We're going to take the limit as n goes to infinity. And again, we could use L'Hopital's rule, or we could just think about which of these is going to grow faster. The exponential function in the numerator, or the polynomial that's in the denominator. And the numerator, of course, is going to grow faster because it's exponential. So we would say this sequence diverges. Take a look at this one. Negative 2, 8 over 2, negative 26 over 6, etc. You can see it's some sort of an alternating series, or sequence rather. And notice that all the numerators are 1 less than powers of 3. So we're going to express the numerator as 3 to the n minus 1. And how about the denominator? You may not recognize that yet, but you're going to see that several times throughout this chapter. Those are factorial. Remember n factorial? So 1 factorial is 1, 2 factorial is 2, 3 factorial, 3 times 2 times 1 is 6, 4 factorial is 24. 5 factorial is 120. So those numbers are going to come up quite a bit in this chapter. We're going to express this as negative 1 to the n, that takes care of the alternating part, and then 3 to the n minus 1 all over n factorial. We're interested in the limit here as n goes to infinity. Since it's alternating, let's use that theorem we talked about earlier, that absolute value theorem. And let's take the limit of the absolute value of this. So in other words, drop the negative 1, the alternating part, and just look at this. And if this goes to 0, that's going to tell us that the original sequence also goes to 0. So it does this. So which of these grows faster? Well, I'll tell you, factorial is like the Superman of all functions. It grows faster than everything else. It beats out exponential. Of course, it beats out polynomials. So 3 to the n, even though it's exponential, is actually going to grow slower than n factorial. So since n factorial is going to grow faster, that means this will go to 0. Since the absolute value sequence went to 0, that means the original sequence also goes to 0. Last thing I want to talk about is monotonic sequences. And last year, we mentioned it. We didn't spend a lot of time talking about it, but I know we mentioned a monotonic function. So a function that was monotonic meant that it was always increasing or always decreasing. So a sequence would be the same thing. All the terms are increasing or all the terms are decreasing. The question here says, determine whether or not this sequence is monotonic. So a sub n is given by 2n over 1 plus n. So think about, what would a sub n compared to a sub n plus 1 look like, the next term in the sequence? If we write out a sub n plus 1, make sure you see what I'm doing here. This is a sub n, then a sub n plus 1, we're just going to replace all the n's with n plus 1, and we get this expression. The question is a sub n always less than a sub n plus 1? I'm going to set up a little inequality here comparing an a sub n term and the a sub n plus 1 term. And do a little algebra here, just cross multiplied. Simplify the terms. You'll notice that I'm just going to simplify down to 0 less than 2. Question is that a true statement? 0 less than 2? Yes, of course it is. It will always be a true statement. So what we're saying here is that each successive term is going to be larger than its previous term. So this represented each successive term, and it's always, no matter what n is, since this is always a true statement, each a sub n plus 1 term is always greater than each a sub n term. That means the sequence is monotonic.